agglomerate, aggregate. So what my PhD student did is she treated multi-volt carbon nanotube with ionic liquid. Again, a very simple chemistry. If you use ionic liquid and if you treat ionic liquid with carbon nanotube, you can debundle them. And you can also make an interfacial contact with SBR rubber. You can see a small cartoon here where you can see the rubber is connected to the carbon nanotube with ionic liquid. What we have used is 1-benzyl 3-methyl imidazolium chloride. And if you look at this transmission electron microscopy, the top part is actually the top one is without any ionic liquid. You can see a circle there. The carbon nanotube forms bundles. And if you look at the TEM at the bottom, we have just magnified one CNT. You can see the CNTs were beautifully dispersed in the SBR matrix. And look at the percolation process we got. AC conductivity as a function of concentration of CNT, you got a beautiful percolation. So we found that if you just put 3% of carbon nanotube, you get very good dispersion of carbon nanotube in SBR matrix, and you get a beautiful percolation. You know what we did? My PhD student, and me with my collaborator, we made soft elastomeric materials for EMI shielding. EMI shielding we need, next slide please, next slide. You can see our EMI shielding data. The shielding, we got very high shielding effectiveness. You can see this is the graph. The shielding effectiveness as a function of frequency. And you can see without ionic liquid, zero ionic liquid, you see the shielding effectiveness is very poor because we could not disperse carbon nanotube well. Suppose the compounds containing ionic liquid, you see the carbon nanotube with the 10 concentration with ionic liquid gave very good data, very good research. So we have a series of patents and we've also published quite a good number of papers. Soft, conductive, elastomeric materials for electromagnetic shielding applications. So many electronic equipments have to be shielded from unwanted radiations. We also made some interesting study with a, next slide please. We also made some interesting study with my French collaborators. Next slide, yes, with the University of Orleans. You can see this slide. You know what we have done? We have taken natural rubber latex. Kerala has lots of natural rubber. So we have taken natural rubber latex. Go back. We have put carbon nanotube into natural rubber latex. Go back, please. And what you really find here is, you see this is the bottommost curve is, you can see stiffness as a function of strain amplitude. Go back, please. The stiffness as a function of, strain amplitude. You can see neat natural rubber. If you put just 1% of carbon nanotube, there is behavior very similar to neat rubber. If you put 5.4% of carbon nanotube, you see there is a dramatic increase in stiffness. The stiffness is very much increased. And you might ask why? Because when you put 5.4% of carbon nanotube in natural rubber latex, and eventually we made a beautiful conductive composite, you see carbon nanotube forms a very strong network. And because of this network, you have an increase in stiffness. 5.4% give very high E dash value. E dash is nothing but stiffness. And you can see the stiffness decreases in a nonlinear fashion with strain amplitude. That means you stretch the rubber, you know what happens? The network is broken. That is why you have a nonlinear viscoelastic effect. Next slide, please. Next slide. What I want to show you is here the storage modulus as a function of temperature. As expected, as you increase the temperature, the modulus values decreases. Next slide, please. Next slide. Yes, the interesting part of this story is when you put carbon nanotube into natural rubber, of course, the modulus goes up, it becomes stiff, and you get nonlinear viscoelastic effect. One interesting observation, the company, we're cooperating the company, they're making artificial skin. You can see these are all very flexible rubber, and the rubber becomes conductive. Look at this, the volume resistivity decreases as a function of carbon nanotube. So we made very soft material. Natural rubber is a very soft material, it's lightly cross-linked. And we have made it conductive. Normally, all polymers are non-conductive electricity, but if you put carbon nanotube, and if you can disperse them properly with brilliant chemistry, you know what you get? You get conductive, elastic, flexible rubbery materials. That is very useful for manufacturing of artificial skin. So we had a contract with the company. Next slide, please. We'll go to the next slide. I will show you some interesting work we have done with General Cables United States. They are the biggest cable company in the US. So we worked with them for about 2 years. And you can see the photograph of my PhD student. She's an assistant professor now in a college. Next slide, please. You know what we have done? The company in the US provides us a series of nanomaterials, aluminum oxide, clay, titanium dioxide, etc., etc. They airlifted all these materials to Mahatma Gandhi University campus. And the polymer material we worked was XLP, cross-linkable polyethylene material. It's a very important material for cable. The American company was interested in underwater cables. So they asked us to mix different nanoparticles together and to put into polymeric matrices. And the first TM picture, what you really see is XLP matrix with aluminum oxide, 5-8%. The second TM picture is XLP matrix with 5% of clay. And the third and fourth, what we did is, my PhD student and I, we mixed different nanomaterials together. Aluminum oxide and clay together we mixed. 1:1 combination and put into XLP matrix. And if you look at the first slide, the top, you'll see when you put aluminum oxide, although it was surface modified, you have a lot of aggregates. Interestingly, when you have a combination of aluminum oxide and clay together, 1:1 ratio, you know what we found? You can see a cartoon here. They self-assemble and form a network inside the polymer matrix. And the polymer is completely immobilized. Next slide. You can see what sort of effect we got. Next slide, please. We got something very interesting data. You can look at the stress strain behavior of this material. You see, the bottommost one is the black one is neat polymer. And the red curve is nothing but the polymer filled with 5% of clay. And just above that, you can see the polymer filled with aluminum oxide. Look at the topmost curve. This is a mixture of aluminum oxide and clay together, total 5-8%. And you can see the dramatic effect. The modulus is a measure of stiffness. You see, look at 812 megapascals. So we showed to the company that it's very important to mix different nanoparticles together. Of course, they are all chemically modified. And if you put into a polymeric matrix, you can get synergistic effect. And the company was interested in water-resistant cables because they were working on underwater cables. And the problem with underwater cable is eventually water will diffuse in. We have 3 cartoons here. Look at the first cartoon. This is actually the polymer filled with aluminum oxide. The second one is the polymer filled with the clay. And the third cartoon is polymer filled with clay and aluminum oxide. Next slide, please. You can see the cartoon. You see the three cartoons you can see. First cartoon, second cartoon, and third cartoon. You can see the diffusion profile. You see the last cartoon where you have clay and aluminum oxide. The polymer is completely resistant to diffusion process. So we made water-resistant cable which is completely impermeable to water. So if you dig a cable for 10 years, water cannot diffuse. So this is the beauty of mixing different nanoparticles. This is the beauty of self-assembly. Of course, you have to do a good chemistry to get this self-assembly process. And if you put clay alone, clay is a beautiful material for resistance to water diffusion. But still, if you use clay and another material, if they self-assemble, if they form a network, you can make excellent water-resistant cables. Next one, please. Next slide. Next slide, please. I will show you some of the work we did with the Department of Space. We had a long cooperation with the Department of Space. You can see my PhD students and my German collaborator. And we worked with the Department of Space, VSSC, on developing super tough materials. Next slide, please. You know what we have done? We worked on a material called epoxy. You can see the beautiful picture of epoxy matrix. It's an excellent material, but the problem with epoxy is the fracture toughness is very low. Crack propagation resistance is very low. If you give a sudden shock to epoxy, it will break, shatter into pieces. You know why? Because it's highly cross-linked. So the mandate given by Department of Space is you make super tough material. Look at the next slide. Next slide, please. You know what we have done? There are different strategies to make super tough material. So we mixed epoxy with different protocols we tried. We blended with different polymers. We put nanoparticles. We put block copolymers. My group actually worked on this topic for the last 10 years. And I will show you some key result what we got. Next slide, please. A PhD student of mine is now an assistant professor in the college. You know what he did? He mixed epoxy resin with different types of thermoplastics. You see, we could generate lots of beautiful morphologies. This is with sand, epoxy with sand. And these morphologies are very interesting. You know, they undergo cavitation process. They can stop the crack. And this is actually the phase separation process, epoxy and sand systems. Next slide, please. Next slide. You know, once you have this sort of structures, you can see a transmission, high resolution transmission electron microscopy picture where you have epoxy system with one small globule of sand. So these structures gave very high resistance to crack propagation. You can see a domain of sand that could really resist the propagation of crack. On the left-hand side, you can see dynamics of phase separation process. We also followed the phase separation using light scattering process. Next slide, please. You can see we have made a variety of structures. We have mixed with sand, with ABS, and we made fantastic microstructures and nanostructures. Some of the structures are nano, some of the structures are micro. And all these new morphologies gave rise to super toughness. Next slide, please. Next slide. So these are all new structures we have developed. You see, you can say quaternary structure. You see the black one is actually epoxy phase, and you have a disposed sand phase, and inside this you have epoxy phase. So we have made very complicated phases by mixing epoxy resin with the different types of polymeric systems. Next slide. We have done something interesting with another PhD work, again with epoxy. We have mixed epoxies with block copolymers. The earlier slide, what I showed was epoxy with thermoplastics, SAN, ABS, etc. This is again an interesting PhD work we did. We mixed epoxy with the block copolymers. You know, block copolymers are very fascinating material. They can self-assemble. And we have shown that when you mix epoxy with the block copolymers, you can make different types of nanostructures, corsal structures, spherical micelle, worm-like micelle, or vesicles. So we generated all these sort of morphologies. The only thing you have to do is you have to play with the block copolymer multiweights, block copolymer composition. I will show you a couple of slides what we got. Next slide, please. If you play with the block copolymer or composition, you can make different types of structures. Look at this. This is a very interesting slide where a PhD student of mine mixed epoxy with polystyrene block polybutadiene. It's a commercial dye block we got from a company. If you simply put this dye block into epoxy, you don't make any nanostructures. You know what we did? We did again a small chemistry. We epoxidized double bond of polybutadiene. When you do that small chemistry, the whole polybutadiene will be solubilized by epoxy because it's epoxidized and epoxy, they like each other. And polystyrene self-assembled. You see lots of dots. These dots are nothing but nanostructures of self-assembled polystyrene with a core of, the core of polystyrene with a shell of polybutadiene. And next slide will give you a very nice cartoon drawn by my PhD student. Next slide, please. Next slide. Yes, you can see this cartoon. You can see that the core is nothing but polystyrene. The block of polystyrene, which is incompatible with epoxy. And you can see the dark macromolecular chains. They are polybutadiene, epoxidized polybutadiene. They interact with the epoxy matrix. So this sort of nanostructures you have made and gave rise to very high toughness. Next slide. Next slide, please. We will show you some of our work on biomedical applications. I have a big group on biomedical applications. We do a lot of electrospinning process. Dr. Robin is now in Qatar. Dr. Gia just left me. Blessy is submitting thesis. Dr. Joshi was in China. She was just back, and Dr. Praveen went to Bangalore. So we have a very active group on biomedical nanocomposites. Next slide, please. You know what we do in biomedical manufacturing, biomedical, one of the ways we do the processing is by electrospinning process. This is our electrospinning system. We are able to make non-woven scaffold material. We do electrospinning of PLA, variety of biocompatible polymers, PCL. We also put nanoparticles into it to have accelerated wound healing. You can see a sacrificial wound we have made. And this wound is, next slide, the wound is closed by a tape. Next slide. The wound is closed by a tape. You can see this. And you know, after a week, you can see the wound is completely healed. This is the beauty of electrospun scaffolding material. You can have, next slide. You can have excellent cell migration, cell proliferation, angiogenesis taking place. So I have a group working on developing wound healing materials made of biocompatible polymers with different types of nanoparticles. Next slide, please. Next slide. You can see the cell migration, cell proliferation, angiogenesis taking place. We also work with guinea pigs. We work with animals with a hospital nearby, thanks to Pushpagiri Medical College, we do a lot of animal work. You look at the in vivo profile of this new wound healing tape. Next one, please. Next one. You see, you can see that the guinea pigs, we made sacrificial wounds and closed the wound with this tape. Next slide. You can see the wound is closed by the tape. You know, after just a week or two, you get beautiful healing action. You can see the electron microscopy picture of our tape we have made by electrospinning process. This is made by PCL and with 1% zinc oxide. And 1% zinc oxide has a beautiful healing action. Next slide, please. You can see a single fiber, a single electrospun fiber we have shown for a better understanding. You can see a single fiber, which is electrospun, and you can see lots of nanoparticles on the surface of the fiber. These nanoparticles have a very beneficial effect on the wound healing process. Next slide, please. So we have tried many different types of nanoparticles, zinc oxide, titanium dioxide of definite size, shape, and distribution. Next slide. But they do this if you use zinc oxide nanoparticles. Zinc oxide nanoparticles have very beneficial effect. Zinc oxide nanoparticles react with oxygen, giving rise to hydrogen peroxide. Hydrogen peroxide has a very good effect on wound healing. Next slide, please. Next slide. You can see the cell proliferation, cell migration, wound healing, and angiogenesis is taking place. So we have very systematically looked at all this process. We have done a tremendous amount of animal studies and in vitro studies. Next slide, please. Another important point of putting nanoparticles. You see, I said if PCL is a very interesting biocompatible polymer. If you use just 1% of zinc oxide, you have accelerated wound healing. You also have accelerated disappearance of scaffold. You know, the scaffolds have to disappear after a period of maybe 2 weeks or 1 month or 2 months. That should not stay. That's a sort of temporary support. If you look at this 2 SEM picture, you will find that PCL with 1% zinc oxide start disappearing after 20th day. So the disintegration of scaffold has been accelerated by the presence of nanoparticles. Next one, please. We also actually quantified the wound healing process. You see, here you can see there are 4 sets of photographs. We have followed the wound healing as a function of time, day 1, day 5, day 10, day 20, day 30. The first set of samples need PCL alone. The second set of samples is PCL with 1% of zinc oxide. That gave rise to excellent wound healing. You don't see any, after 30th day, you don't see any scar. So we are able to make wound healing without any scar formation. You can also see the positive and negative control. And if you look at the quantified data, wound healing as a function of number of days, you will find PCL with the 1% of zinc oxide gave the best result. So we have shown that electrosponge system with a very small amount of nanoparticles have excellent wound healing activity. We have worked with a large number of polymeric systems. Next slide, please. I have a big group working on biological nanocomposites or bio nanocomposites, extracting bio from nature. The former speaker actually talked about bagasse. So what we do is we take agricultural waste. It could be coir, it could be bagasse, it could be jute, or it could be sisal or pineapple leaf, and we extract nano materials from this. I have lots of collaborators in Brazil, in South Africa, in Sweden, and many PhD students. Right now, Dibu is in France, and Peter defended the thesis, although he's in the US. So we have lots of collaborators on bio nanocomposites. Next slide, please. Just show you a couple of slides what I do using bio nanocomposites. See, we extract bio nanomaterials from agricultural waste. And effectively, we make nanocellulose. And we make it, these materials, we make use of nanocellulose for photonics, composites, medicine, modification, manufacture of films and foams for multiple applications. Next slide, please. If you look at my next slide, you can see this is a slide I borrowed from Alain Dufresne from France, my great collaborator. He's probably #1 in the world in the area of bio nanocomposites. So Professor Dufresne has derived nanomaterials from different biological sources. Wheat straw, cotton, waxy maize, crab shell. Crab shell, you can make beautiful nanochitin. So he's a very brilliant researcher. He showed the world that waste is something very useful. So we followed his protocol and we extracted nano from a variety of bio waste. Next slide, please. I'll show you just a couple of slides what we're doing. This is something very interesting we did. A PhD student of mine currently doing a postdoc in France, he took panning, polyaniline. You can see this round bottom flask, panning inside. Sorry, round bottom flask, what we have taken is nanocellulose solution. This is nanocellulose extracted from a pineapple leaf fiber. See, this is nanocellulose. We manufacture nanocellulose in our laboratory. Then he injected aniline into it. And we went for in situ polymerization process. You see, very simple protocol. And then we went for a vacuum filtration. Simple vacuum filtration. Followed by hot pressing. You know what we have made? We have made conductive, thin conductive paper, which is extremely conductive. And we have made 1 mm thickness, 0.5 mm thickness. And this is a very interesting material for EMI shielding applications. See, starting material is very simple. Nanocellulose from pineapple leaf. Next one, please. My PhD student demonstrated this in our laboratory to look at the conductivity. You can see the EMI shielding effectiveness, 0.75 mm and 1 mm. You see, look at the shielding we got. Protect our electronic instruments from different types of radiations. Look at EMI shielders have lots of applications. We could get 16 dB shielding. And this case we got, if you make 1 mm thickness, we got something like 24 dB shielding. So we made lightweight, very thin, conductive EMI shielders, starting from pineapple leaf waste. Next slide, please. I'm winding up with a couple of slides. If you look at the next slide, you will see another PhD student of mine. He also showed the different same protocol. He took pineapple leaf suspension And then, you know what he did? He introduced aniline, the same way what Debu did. And then he went for in situ polymerization. Instead of compression molding, he went for a freeze drying process. When you go for a freeze drying process, you know what we got? We got lightweight form. We made aerogel. You can see our recent paper in carbohydrate polymers, Piney CNF conductive aerogel. Conductive aerogel is a marvelous material, very lightweight, very low density, and is extremely conductive. Next one, please. In the next slide, you will see the EMI shielding effectiveness of this material. And he also gave a beautiful interaction between nanocellulose and tiny. This is a strong hydrogen bonding interaction. We could show this by infrared measurements. The interaction between nanocellulose and tiny is quite strong. Next slide, please. And you will see the EMI shielding effectiveness of the material. Look at this, the shielding effectiveness. We could make something like 30 dB shielding effectiveness. Slightly better than what Debu made. The gentleman's name is Avinash Pai. He made excellent shielding material. We are actually filed for patents, and the paper is also published now. It has come out now. So we are able to make beautiful material from agricultural waste by combining the agro waste with a polymer. Next one, please. My last slide is functional polymer nanocomposites give a lot of opportunities. Combining a polymer with a nanoparticle, you can make brilliant nanocomposite. But chemistry is very, very important. You have to do a good interface chemistry. Otherwise, you cannot make any functional material. And if you do that, you can make exotic battery materials. We have showed the tire company, cable companies. You can increase the stiffness, strength, toughness. That's what I mean mechanical reinforcements. We are able to make good electromagnetic interference shielding material. Lots of applications. We are working with many companies for shielding. Conductive elastomers, which are stretchable. I did not show you the water purification sensor application. We also did a lot of water purification. The previous speaker from South Africa spoke about water purification. We brilliantly made use of nanocellulose membranes for water purification, removing dyes. I mean, bacteria, virus, and nanoparticle or metal particle in water. We also made beautiful sensors. And you can manufacture biomedical wound healing materials out of this. Next slide. Next slide, please. I would like to thank my funding agencies, particularly Professor Sena Rao, for the generous funding from the Nano Mission. We could establish a state laboratory in the campus on nanoscience and nanotechnology, the support of Professor Sena Rao, and my thanks to him. And ISRO, CSIR, DBT, ICT, DRDO, DIT, Academy of Sciences, BRNS, we got funding from large number of sources. General Cables, United States, Surface Street, Czech Republic, Apollo Tires, MRF Tires. You can see my collaborators, Didier Rupsel from France. We do a lot of, biological work. Yves Grohens, conductive elastomers, Piontech. We did a lot of super tough material. Daniel Plaspini in Brazil. We did a lot of water purification with his collaboration. Pula Modernas. We do a lot of rheology with her. Nandakumar Kaldriklu is my collaborator in the campus. Right now, he's heading the Nano Center. And hard work of all my students are very much appreciated. Next one, please. You can see my group in chemistry. And you can see the my visitor from, our visitor from France came. Then we have a photograph. Next one, please. Our group in Nano. You can see our present director of the Nano Center. We have a big group in Nano. We have students from Africa, we have students from Malaysia. So we have a good international, group here at the Nano Center. Next one, please. Next one. Those who have not visited our campus, most welcome. Our campus is quite a beautiful campus. The size is 100 acres of land, and we have around 1,000 students in the campus. I'm attached to chemistry and Nano Center. Next slide, please. Some beautiful pictures of Kerala. Those who are from outside India should visit Kerala after pandemic. It's a very beautiful part of India. We have beautiful canals, backwaters, boatways, Kathakali, traditional art of Kerala, very old temples. This is God's own country, very beautiful part of India. Very welcome to Kerala. So I invite all my colleagues from abroad to visit Kerala after the pandemic. Next slide, please. I'm also an editor of nanostructures and nano objects. Those who do very good quality work in nanostructures and nano objects can submit your articles to this journal. The site score is now 5.6, and they'll save your traditional journal no fees. So those who do really good work in nano, please send your papers to nanostructures and nano objects. Next one, please. We have a conference coming up, international webinar on 100 years of macromolecular science. Probably some of you know that the concept of macromolecules introduced 100 years ago by the German Nobel laureate, Hermann Staudinger. So we are celebrating 100 years of the existence of macromolecular science in the campus, 11, 12, and 13 of November. This is an international webinar. Those who are really interested, please send your abstract for this international webinar, celebrating 100 years of macromolecular science. Next one, please. We also have a conference coming up next year. This is a face-to-face meeting, international conference on nanomaterials. I hope the pandemic will be over by the time, April 9 to 11, 2021. This beautiful scenery of the backwaters of Kottayam. Next one, please. Thank you so much. I think this is my last slide, and many thanks for the kind attention. Thank you.
Thank you very much, Professor Thomas, for your informative talk. Sorry, I think there was a time lag between my slides moving and the talk.
I understand. Yeah, it happens sometime, because you couldn't see the slides well. Yeah. So
yes, sir. So I think we have time for a couple of questions. If anybody want to ask Professor Thomas, please you can raise your hand. I'll call you. Okay, I see Professor Padmanabhan.
Thank you so much, Professor Thomas, for agreeing to. I know you're busy. You're in the office now. I know that people are around you, and thank you very much for taking time and then sharing your. I would say that very multivarious researcher. I mean, you research working in multivarious fields and versatile applications of your nanocomposites. And I just have a small question actually. You talked about PLA said and no composite for wound healing. I think it's appeared in scientific reports. I'm not sure actually.
Yes.
PLA said and no composites.
We published in
And
scientific
I
reports.
noticed that you electrospin it actually.
Yes.
What's the purpose of? I mean, can't you apply it directly, without spinning and getting the fiber out? Actually, is there an issue with that? Perhaps I think they use the fiber because that will, knit the wound or rather close the wound. Is that purpose you want to have the fibers on? Otherwise, you can apply directly because adeno is the antibacterial one, and PLA is the matrix. So what is the purpose of spinning it? Is it for scar removal so that you don't have any scar at all? Am I audible?
Yes, this is a very interesting question, Professor Padmanabhan. You know why we have went for spinning? There are multiple purposes. When you go for spinning process, you generate a large number of fibers, so you have an extremely high surface area. Second point is you can make pore structure. For a tissue growth, we need macroporosity and microporosity. This is very important for giving, nutrients to the tissues and also to siphoning out the waste. So if you go for electrospinning, you can make a very high surface area matrix. That's number one. Number two is that porosity is extremely important for tissue growth, tissue regeneration. That is why porous structures are extremely beneficial for wound healing. That's why we went for electrospinning. Okay. If you make a film, it's not very active.
Okay, and another short question is that your natural rubber CNT nanocomposite, and I saw a very good dispersion with your 5% carbon nanotube in that one.
Yes,
beautiful nanotubes coming. Very well dispersed. I'm just wondering, did you do any kind of functionalization of a CNT?
You see, what we have done is we have actually did a coating with DNA, with carbon nanotube.
DNA?
Yes, DNA, yes. And then we actually covered carbon nanotube surface with a biological coating. And these natural rubber also has protein. And that was a very interesting combination.
You did the latex or in the
latex? Latex is beautiful. Okay. The advantage of latex is the dispersion is much easier.
Okay.
Once you put dry rubber, the viscosity is tremendously goes up. You have water medium, you have dispersed rubber particles, and you have protein, and that's a very interesting. So we have actually covered.
Otherwise, natural rubber, poly isoprene. So that for that one, if you want to have that,
you have to really
latex one, but other one actually probably you'll have to functionalize with for example, alkyl group, a long alkyl group.
Exactly.
And you have a better compatibilization.
Exactly, you are right. You have to have, you have to have ionic liquids, or you have to put alkyl groups on the surface of, these carbon nanotube, because carbon nanotube, when you put in rubber, they bundle. So you have to debundle them. And then you have to have, as you rightly indicate, you have to have connectivity between carbon nanotube and rubber. Yes. Otherwise, you don't get any improvement.
Yeah.
A fantastic question, Naveen. Yes.
Thank you so much, actually, for taking time.
Thank you.
Then I know you're very busy there. Naveen, you can. Thank you.
Yes, are there any more questions?
Can I ask a short question, sir?
Yes.
Myself, Adarsh. Yeah, sir, it's a very nice presentation. So I want to ask you the same regarding the wound healing. That's why just a small question. It's a kind of technical question. Because in the electrospin method, I wonder all the polymers give the same result, sir? I like it, a kind of clean sheet of fibers.
It's a very important question. These are electrospinning. You have a number of parameters. The viscosity of the polymer.
Yeah.
You have to dissolve in a suitable solvent.
Yeah, sir, that's another one, sir.
It's very difficult to be electrospun. You have to have a good solvent.
Okay.
And then, you can do a lot of other things. You have the spinning arrangements, the voltage you're applying, the moisture content. So
that means every polymer has their own some like reported parameters for it.
You have to really optimize. You have to really lot of optimization to get beautiful fibers. But one important point I wanted to tell you is when you use polymers for wound healing, we have to be extremely cautious because we have to select only biocompatible polymers.
Yes.
You cannot use nylon, you cannot use polyester, they are not biodegradable.
Sir, but that's why another question is that if you are using the biocompatible polymers such as like a kind of PLGA sort of polymer, but the solubility of those polymers in the polar solvent is very high. So these polar solvents can be used in for this purpose, like acetonitrile or more polar solvents.
This is again a very interesting question. The solvent that we are using is completely removed.
Yeah, that's
there should not be any residual solvent. That's very, very important because we are dealing with biological tissues.
Yeah.
And you also have to select solvents which are not toxic. Very important. If a smaller residual solvent, if it is occluded, it can give you deleterious effect. So when you do electrospinning for wound healing application, you have to be extremely careful about the nature of the polymer, nature of the solvents, and nature of nanoparticles you're selecting. The shape and distribution of nanoparticles. You see, I pointed out zinc oxide of 50 nanometer size. If you use zinc oxide of 10 nanometer size, all tissues will die.
Okay.
So we have to be very, very careful about this. It's a very interesting question you raised.
Okay. Thank you. Thank you.
Question.
Yeah, sir. Thank you.
Okay. Thank you, Dr. Adarsh. Are there any more questions? Okay. If not, I think we are running out of the time. Let's all thank Professor Thomas for his wonderful talk. In spite of his busy schedule, he took a time for us. We are very grateful for you for that. So thank you. Thank you very much. Okay, so this is the end of the morning session. So I hope you all actually enjoyed all the talks and you got some take-home messages. So we will take a short lunch break. So we will be reassembling at 2 o'clock with the talk from Professor Suresh Pillai. He will be joining us from Ireland. So I request everybody to come back, you take a lunch break and come back at 2 o'clock so that we can start with the session. And then after the talk, from 3 to 5, we'll be having these oral presentations. Today we are having 2 streams running parallelly. We have inorganic chemistry and the electrochemistry streams. And so all the participants are requested to actually choose the different stream link provided to you. Then you can actually log in and then attend all the presentations. So we have stream 1, which is inorganic chemistry, which will be chaired by Professor Shaktivel from Central University of Kerala, Kasaragod. And then stream 2 will be electrochemistry, where we have Dr. Leena from QSAT chairing the session. So see you all again at 2 o'clock. You all have a nice day.